Well, I can't believe it, but here we are on the final unit of the course. So we're going to start off by introducing the idea. So most of this course is going to be related to triangles, really circles, but triangles in essence. And in order to do a lot of this stuff, we're going to have to remember a lot of rules that you've come across over the years. Now, most of this unit is going to be the idea that there's going to be a number of these laws or rules, I should say, and theorems and such that are going to apply to all the various problems. Sometimes they're going to be word problems, sometimes they're going to be straight knowledge math problems, okay? But there is going to be a lot this unit. So you have to really take the time, make sure you're doing your practice work, because you are going to not have them at the tip of your tongue if you haven't been doing that, because they won't all be provided for you on each assessment or anything like that. So you need to be able to pull from them when you actually need them. So let's start off by going through some old angle theorems that you learned a while ago. So first off, if I have two crossing straight lines, and the opposing angles on the opposite sides of those lines, let me just go back to my draw here. So we have an angle here and an angle here. Those two angles will always be equal. So angle A will always equal angle B. Similarly speaking, this angle would be equal to that angle because it's across from it. We call this the opposite angle theorem, or OAT. There's lots more that are just like this. The next one, so let me just highlight this. The next one is called the supplementary angle theorem. So the supplementary angle theorem is if you have a straight line and then another straight line coming from that straight line at any angle, the two angles on the opposite sides of that second line will add up to be exactly 180 degrees. Because we know that a straight line, if you do the angle from the left all the way around to the right, if I do an angle from here all the way around to there, that's half a circle. So that's 180 degrees. So that means that angle C plus angle D must be 180 degrees. So we call this the supplementary angle theorem, SAT. Okay, so the next one is very similar. This one is called the complementary angle theorem. So this is similar, except it's not a half a circle, it's only a quarter of a circle. And we know the angle of a full quarter circle, from here all the way up to here, is exactly 90 degrees. So if it's 180 here for a half a circle, then the quarter circle is 90 degrees. So similar to the last problem, in this case, angle E plus angle F are going to add up to be exactly 90 degrees. So angle E plus angle F are going to be 90 degrees. That's a 9, not a 7, I swear. Okay, so we call this the complementary angle theorem. Now, another one that you learned ages ago is that all the sides in a triangle add up to be 180 degrees. So we call this has a special name, we call this the angle sum of a triangle theorem. Oh my goodness, that is quite the word. Angle sum of a triangle theorem. Shortened down, ASTT, angle sum triangle theorem. So that means all three angles add up to be exactly 180 degrees. So in this case, angle I plus angle G plus angle H are going to be 180 degrees. Now, knowing all of this information, and the next one actually, most of these today, what they're going to help us do is they're going to help us determine unknown angles. So if we know some of these properties and we're given a diagram, we might be able to get some new data out of that diagram simply by knowing these rules. So the next one, we have an isosceles triangle. So in this isosceles triangle, we know that two sides are going to be equal. But because they're equal, that means that the two angles at the bottom where those two sides separate are going to be equal as well. So we call this the isosceles triangle theorem, or ITT. Okay, so in this case, angle J is equal to angle K. This is the ITT. Alrighty. So the next one, this is an interesting one. This is probably one of the more powerful ones. So this is what we call the parallel line theorem, and this parallel line theorem can actually be broken up into three separate theorems within. So imagine you have two parallel lines, and you have one line that intersects and crosses both of those lines. What this does is this creates a variety of different patterns, and those patterns all share certain properties. So the first one that we see is what we call the Z pattern. It's called the Z pattern because if you draw a line, we got the top, Oops. So let me go diagonal. We got the diagonal, and then we got the bottom. We have a Z pattern there. So that Z pattern, let me just undo that. That Z pattern, come on, undo. There we go. That Z pattern creates a property where the two inside angles, this angle here and this angle here, so angle L and angle M, are equivalent. Okay, let me just write this out. So angle L is going to be equal to angle M. And the way that we write this as parallel line theorem, so PLT dash Z. So we call this the Z pattern, okay? The Z pattern. You can see that it's alternate angles. It means the opposing angles on the inside of the Z. Okay, so the next one is the F pattern. Similarly speaking, you look for that shape of an F. So there's the back of the F, there's the first arm, and there's the second arm. There is the F pattern. What this tells me is that the inside angles of each arm, so the N and the O, those two angles are also equal. They will always be exactly the same. Oh, I got one more to undo there. There we go. So in this case, angle N and angle O are equivalent. Now, you could go upside down with the F as well. So for example, the angle here is going to be equal to the angle here. That's the same thing. It's still an F. It's just been rotated because this is just a shape. Shapes can be rotated, right? Doesn't change the shape to rotate the shape. So in this case, this one is called the parallel line theorem, PLT dash F for the F pattern. And the last one is the C pattern. So we're looking for a C shape. In this case, we see a C shape right here. It's a little bit off kilter, but it is definitely a C. There's our C. What it's telling us is that those two inside angles, angle N and angle M, will add up to be exactly 180 degrees. Right? They don't match. They add up to be 180 degrees. So angle N plus angle M is going to be 180 degrees. Lots of data here. So this is the parallel line theorem, C. So there's a whole lot of little rules in there that we have to remember. And when we do so, it's going to reveal a lot of data about all the problems that we have going forward. Okay, so let's scroll down a little bit and apply this. So imagine we have this problem here. I don't know why it's all off kilter there. Okay, so imagine we have this problem here, which looks exactly like our issue up here. All right. So what it wants us to do is find the value of each angle, angle A, B, C, D, E, and F. Now, some of these can be solved in more than one A, but let's start with, more than one rule. Let's start with angle A. What rule can we apply? Well, we have a straight line, and then we have a line that goes through it. So angle A plus the 151 will give us 180 degrees. That's the supplementary angle theorem. So the SAT. So in this case, angle A is going to be 180 minus 151. So 180 minus 151, which is equal to 29 degrees. This is the supplementary angle theorem. Okay, let's go to B. Well, we look at B, we see two intersecting lines, so that means that A and B are opposite sides of each other. That's the opposite angle theorem. So angle A is exactly equal, angle B is exactly equal to angle A, which is also 29 degrees then. This is the opposite angle theorem. Now we go to C. C is opposite of 151. So we can actually do this one as well. I should go back actually. So for B, we did the opposite angle theorem, but we actually could have done the supplementary angle theorem as well because it's supplementary with the 151. So it still would have been either or. So we could do both. I'm going to say OAT or SAT, opposite angle theorem or supplementary angle theorem. Sorry, let's go back to C now. So C, again, you could do supplementary angle theorem with A, or we could do opposite angle theorem with 151. I'll tell you that opposite angle theorem is always the better choice because that means you don't have to do any calculations. Supplementary angle theorem, you have to do a calculation and you may perchance create a mistake. So we're going to say this is 151 degrees and this is going to be the opposite angle theorem. Great. So let's keep going. Now we got to go down to D. D. D's got no angles around it. Ah, it does. It doesn't, but it does have a pattern. It fits perfectly into the F pattern. So the D is below the bottom arm of our F here, and the number below the top arm is the 151. So the F pattern says that those two angles are identical. So D is 151 degrees, and that's from the parallel line theorem, F pattern. Great. E, well, E is just opposite to D. So that means we can use the opposite angle theorem. Great. So we have 151, and that's the opposite angle theorem. Now, the interesting thing is we actually know B as well. So we could have actually used the C pattern with B, or PLT C pattern with B. And that would have gave us the exact same results as well. Awesome. And finally, we have angle F. Now, angle F could be the C pattern with the 151. It could be supplementary angle theorem with E. So we could choose what we want. Since we haven't done an official C pattern, we'll do the C pattern this time. So this one is going to be this one's going to be 29 degrees as well, because we know that a C pattern says that the two interior angles of the C add up to 180 degrees. So 151 plus what gives me 180? Well, 29 again. So this is going to be the parallel line theorem, C pattern. Awesome. So we were able to get every single angle in there. And if you look at it, the only angle that we actually have written on that diagram is 151. But we were able to calculate 6 more angles. We could have done the one at the bottom here too and got every single possible angle in here. Maybe that would have been a G, and that would have been opposite angle theorem with F. So we can get everything. We just need one. We just need one. All right, let's keep going. Let's actually do a little bit of problems here. So find the values of the following angles and state the reason. So it's looking for angle X and angle Y. I can't really do angle Y right now because I don't have enough information, but I can do X. I can see that this is an isosceles triangle. We see that the two sides are equal length. So the isosceles triangle theorem says that the bottom two interior angles are also equal. So that angle X is going to be equal to 40 degrees. And that's because of the isosceles triangle theorem. Awesome. Sorry, my page is just not cooperating here. So that's because of the isosceles triangle theorem. Okay, but since I now know that X is 40, that means I can calculate Y, because the complementary angle theorem says that X plus Y are equal to 90. So 90 minus 40 gives me 50 degrees. So that means that Y is equal to 50. And this is going to be the complementary angle theorem. Okay, so now let's take another step forward to more knowledge that we learned ages ago. The Pythagorean theorem. We all remember the Pythagorean theorem. Given a right triangle, the sum of the squares of the two smaller sides is equal to the longest side squared. Well, we know this written as this, a squared plus b squared equals c squared. And this has a name, which is the Pythagorean theorem. Let's see if I spell this right. I don't have a lot of confidence on that one. Pythagorean theorem. I give myself about 60% odds on that. We'll see. Anyways, so what it's telling us is that we can use more rules to solve more parts of our triangle. Now, in this case, in order for this to work, it needs to be a right-angled triangle. It has to be a right-angled triangle. That is the most important part of this. So if that's true, then we can simply apply a squared plus b squared is equal to c squared. Well, in this question right here, we have two arms of the triangle as 8 and 6. Now we know that the hypotenuse, the C value, is always opposite of the 90 degrees, always of the right angle. So our equation, a squared plus b squared is equal to c squared, applies. We got a 90-degree triangle. The c is going to be our x value, and the a and b, it doesn't matter which is which. Triangles can be rotated. So let's say the a is 6. So this is going to be 6 squared plus 8 squared is equal to c squared. So we have 36 plus 64 is equal to c squared. 100, that's 100, is equal to c squared. But in order to get rid of that square, I got to take the square root of both sides. So the square root of 100 is just 10. So we just end up with c is equal to 10. Now, technically speaking, we know that when we take the square root of both sides, that that's actually a plus or minus 10, but we know a negative 10 is an impossible value, so we don't even bother with it when it comes to geometry. It doesn't make any sense to do so. All right, let's go on to the next one. Same problem, but now our known data is different. We still have a squared plus b squared is equal to c squared, but we know c this time. So that means either a or b is our unknown value, but it's still the same logic. So we have, let's say this is, just to write these out, let's say that's A, that's B, and this will be C. C is always opposite of our 90 degree. So that means I have 7 squared plus x squared is equal to 15 squared. So I'm going to bring that 7 squared over to the other side. So I have x squared is equal to 15 squared, which is 225, minus 7 squared, which is 49. So I have x squared is equal to 176. Now I got to get rid of this square. That means I need to take the square root of both sides. So I have x is equal to the square root of 176. And unfortunately, that's not a nice number. So we're going to say x is approximately equal to, if you put this in your calculator, you should get about 13.3 rounded to 1 decimal place. There we go. So that's our Pythagorean theorem. Okay, we still need more knowledge. We need to know how to work with fractions, okay? We are going to be dealing a lot with fractions this unit, way more than you like, but that's the way it is. When you're given an equivalent fraction like this, we can go through the long way, all right? So imagine I have this. X over 3 is equal to 5 over 30. Now imagine I'm trying to isolate for x. That means I'm going to multiply the right-hand side by 3, so that's going to be x. I'm going to multiply both sides by 3. But when I do that, these 3's cancel out, and over here, we still get the 3 over here. So it becomes x is equal to 3 times 5 over 30, and x is equal to 15 over 30. X is equal to 1/2. Okay? Now, this is great when the numbers work out nice and neat like this, but they're not always going to work out nice and neat like this. So another strategy that we use simply something called cross multiplying. So if I have x over 3 is equal to 5 over 30, okay, without thinking about it, what I'm going to do is I'm going to have my left side equal to 30x, and my right side is going to be equal to 3 times 5. Now I can isolate by bringing that 30 over to the other side, and it's 15 over 30. And x is equal to 1/2. Now, in this small, simple version of the problem, I didn't really save anything, but in more complicated versions of this problem, you may find that it saves you a couple steps and makes the math a little bit simpler. So this is what we call cross-multiplying. So it's, I guess the arrow goes technically both ways. I like to bring the first one, x times 30. So that's going to be my left-hand side. And my right-hand side is going to be 5 times 3, which is going to be on the other side. So we can do the same thing over here. We'll do the exact same thing. So we have 30x is equal to 3 times 5. Okay. And we have x is equal to 15 over 30. And we simplify to the x is equal to 1/2. We can do the same thing over here. Let's cross multiply. So we have 18 times y. So we have 18y is equal to 7 times 4. So we have y is equal to 28 over 18, which y is equal to, we can divide that by 2. We end up with 14 over 9. So it's not really a great number, but it's a number. And we end up with both of our answers. So that's a pretty straightforward way to do it. Is just cross multiply, cross multiply, cross multiply. And it should make life fairly easy, hopefully. All right, so the next one. We're almost done for our review. The slope m, we know that. We've covered that a million times this semester. The slope m of a line segment is the ratio of its rise over what? Rise over its run. Now, we're going to deal with this quite a bit over this semester, so we need to understand what this actually represents. So that means find the slope of the following segment. Our rise, so our slope, is our rise over our run. Well, that's the equivalent of 10 over 12, right? Which just gives us 5 over 6. Why is this important, Mr. Lane? Because I'm going to tell you that we are going to be calculating that quite a bit. Okay, we're just going to make it look a little different as the semester or as the unit goes on. So that's it for our review topic. And tomorrow, or the next lesson, I should say, we're going to get into the actual lessons and start our trigonometry.